Alright, well, hello again, guys. Let's go ahead and round this out. Let's go ahead and finish up evaluating limits analytically. I've gone through a couple of my resources and pulled out some more questions that are more or less are typical in terms of the evaluation of limits analytically using the strategies that we know in order to change the form of an expression without changing the value. And of course, we get into that situation when we approach a limit problem that we cannot evaluate by simply plugging in, and that's because it has the indeterminate form. And we talked about various examples, and let's go ahead and recap those examples. Number one, we have ones that factor to solve. Do I have that volume on? Okay, let's go ahead and shut off volume again. Sorry about that, guys. We factor to solve, and of course that is one that is rational and has a hole in it, or what we refer to more technically as a removable discontinuity. The second type that we talked about was not factoring to solve. It was the multiplying by the conjugate over itself. So it has to do with rationalizing one aspect or another of a rational expression. Okay? And that, of course, is multiplying by the conjugate over itself. Okay? Now, the third type that we discussed had to do with simplifying a complex fraction. Okay, and the last one that we did, I didn't give a specific name to it, but for lack of a better word, it is a rational expression that has been decomposed into its partial fractions. So it's one that has not yet been pushed together. So partial fraction, or sum or difference of two rational expressions, sum difference of rational expressions, whatever you want to call it, okay? It was one that we had to, where it was a sum or a difference of two rational expressions, and we had to push it back together, right, by finding a common denominator and all sorts of fun stuff like that. What I would like to do at this point is I'd like to run through a couple of those examples, but not necessarily in any specific order. I want to go ahead and run through some examples, and even some that actually combine some of the elements of one or more of these particular strategies. Okay, so let's go ahead and jump right in. Let's go ahead and jump in with one that actually does do that. So let's say the limit as x approaches 4 of 1 over root x minus 2 over 1 minus root 2, all of that over x minus 4. Actually, that's a really bad example. Let me find another one. Let's go ahead and deal with, okay, here's one that's really good, that's of the same variety. Let's say as x approaches 0 of 1 over root 1 plus s minus 1 over s. Okay, now we have two problems, right? In the original one where we had a complex fraction, we only had one problem. The problem was, of course, the complex fraction. But now we have two problems. We have a problem with the complexity of the fraction, meaning that I have a fraction within a fraction, but we have a second problem. We have a problem with the fact that there's a radical in there as well that's causing some problems. So we got to figure out what to do first. Well, obviously with the radical in the denominator right here, that's not a whole lot of fun to deal with. Let's go ahead and get rid of the complex nature of the fraction first. And the way we talked about that last time is whatever the problem is, and in this case the problem is the root 1 plus s, or sorry, make the variables agree, that would be a really good idea. 1 plus s, root 1 plus s in the denominator. So how do I undo root divided by root 1 plus s? Well, I multiply by root 1 plus s. And I get the limit as s approaches 0 of 1 minus 1 plus root s, all of that over s times root 1 plus s. Now, the major mistake that will be made here when you multiply by the conjugate over itself is you will forget to include that factor in the denominator in that next step. You'll be so worried about making sure that you distributed this one correctly across that you'll forget to actually include this one in the denominator. I've seen it time and time again. In fact, some of y'all probably made that last spring when we made our first foray into limits. Now from here, this is still a problem. Because when I plug in 0, I still get the indeterminate form. I still get 0 over 0. But now that I've gotten rid of the complex nature, now I can deal with the rationalization aspect of it. Okay? And I can multiply by the conjugate over itself. Now that makes this new denominator awfully, awfully messy. But who cares, right? As long as you're careful with your notation, which after, the years that you've spent with me, you should be, okay? This shouldn't be all that big of a deal. Remember, we multiply by the conjugate because we're employing the logic of the difference of two squares. So when I multiply this, it'll be very quick for me to get right to here. 1 minus 1 plus s. And then I just have to make sure I carry all of the factors appropriately in this new denominator. Okay? Now, when I distribute this negative into this 1 plus s, I'm going to get 1 minus 1 minus s, right? So basically I can simplify this and it's negative s, okay? Now, that is still 0 over 0, but now that right there will cancel with this s, leaving a negative 1. So now I can plug in, I'm going to plug in a 0 into this s and a 0 into this s. When I plug in a 0 into this s, I'm going to get root 1. Okay, well that's, doesn't really matter to us because 1 is, when it's multiplied by anything, is the identity property. I'm going to go ahead and plug in 0 into here, and I'm going to get 2 in this denominator. So this limit is actually negative 1/2. And you see basically the blending of two of the strategies that we've used. We see the rationalization by means, or the dealing with a complex fraction by multiplying through by whatever those denominators are, or in this case the denominator is, since there's only one. And then once I've gotten rid of the complex nature of the rational expression, then I need to deal with that radical. I need to sort of unradicalize that numerator in order to free up that s such that it cancels with the s in the denominator, thereby eliminating the indeterminate form and giving me my limit. Okay? Now let's go ahead and do another one. We won't do one again of that specific variety. If you want to do more of that variety, you can just comment on the blog or you can send me an email or something like that. For those of you who have stumbled upon this video on YouTube, instead of actually being one of my former students, you're just kind of out of luck. So, sorry. Hopefully it'll come up again in a later video or something like that. Or, of course, you can always go to Just Math Tutoring or Khan Academy. Those guys are really, really good. Okay. Now, this one is obviously just a straight up complex fraction problem. Okay, if I were to plug in 0, I don't even get the indeterminate form 0 over 0. I just get a whole lot of mess, right? I get a whole lot of undefined, undefined, undefined. Okay, because I get 3 divided by 0, 2 divided by 0, plus 1 of 5 divided by 0. What I want to do from here is I want to go ahead and eliminate the complex fraction. And you could get a common denominator down here and then use the common denominator and all that sort of fun stuff. I do not like that, okay? The whole problem with the complex fraction is what is being divided by within the larger rational structure. And how do we undo that divided by? How do we undo divided by x squared? Well, we multiply by x squared. How do we undo divided by x squared? Well, we multiply by x squared. Now I can do that because that is essentially 1. And to multiply by 1, that's the entire reason why you learn the multiplicative identity property, right? Now, how do I get rid of x? Well, x is going to take care of itself already because I'm already multiplying by x squared. Now, dealing with the numerator here is actually very, very easy because I know that when I multiply the x squared times the 3 over x squared, I'm just going to get 3. In the denominator, I have to be a little more careful, but the notation really isn't all that big of a deal. When I multiply x squared by 2 over x squared, I'm going to get 2. When I multiply x squared by 105 over x, one of these x's cancels, the other one does not. Okay, and now it is no longer in a form that is, for lack of a better word, icky. Okay, that is, of course, very, very technical math language. I now can plug in 0 in for the only x that is still available, and I get 3/2. Okay, now let's go ahead and do a few more problems. Okay, so we have the limit as x approaches -1/2 of 2x plus 1 over 2x squared plus 3x plus 1. Okay? Now, what type of problem is this? Now, we know that it's not dealing with something that is a sum or difference of rational expressions. This does not look like, that expression does not look like the result of decomposing into partial fractions, right? So it's not that. We know it's not a complex fraction because there's no fraction within the fraction. There is no radical, so there's no need to multiply by the conjugate over itself, but it is still indeterminate. Because if I were to plug in -1/2 into here is -1 plus 1, that's 0. -1/2 into here, -1/2 squared is 1/4 times 2 is 1/2. That 1/2 could combine with that 1 to become 3/2. And when I plug -1/2 into this middle term, I get -3/2. So that's 0 in the denominator as well. Our only hope for this one, with the knowledge that we have at present, is to go ahead and see if it factors. And indeed, this actually is a very straightforward quadratic factorization in the denominator. It winds up being 2x plus 1 and x plus 1. And if you don't believe me, then you need to go back and review your factorization techniques. Okay, and of course that in the numerator cancels with that in the denominator, leaving a factor of 1 in the numerator. And when I plug in -1/2, -1/2 plus 1 gives me a positive 1/2 in the denominator. And what is 1 divided by 1/2? How many halves go into 1? Well, the answer is, of course, 2. Okay, well, let's go ahead and do another one. Let's do one that's a little less straightforward, meaning that it's not quadratic, but it still is a factorization problem. Ruh-roh! Okay, now, this type of factorization, well, it is quadratic, but it isn't quadratic. It's sort of what I always call quasi-quadratic, right? Because it has an exponential form to it, and it might be a little bit easier once we change that and remember that 4 to the 2t is 4 to the t squared, okay, and that's 1 squared. We're not really used to thinking about 1 as a perfect square, but it is. And we see the fact that this in the numerator is 1 squared, 2 squared. Oh my gosh, it's the difference of 2 squares. And therefore I know that that factors rather nicely into 4 to the t plus 1, 4 to the t minus 1, over 4 to the t minus 1, boom, boom. And now I have what? The answer is 1, right? No. What mistake have you made if you think it's 1? You've been treating exponents like it's multiplication. Common error. But when I plug in 0, what's 4 to the 0? What's anything to the 0? It's 1. Now, of course, I hope that you remember why anything to the 0 is 1. And if you don't remember, it's because it implies a ratio of a number over itself. Okay? Let's do one more. We're coming up in about 14 minutes here, and I want to make sure that I don't make these too long. I have 1 over h plus 2 squared minus 1 over 4, all of that over h. Okay? Now, this particular one is, of course, very, very straightforward. It's the same style as ones we've seen in the past. And what we want to do is we want to get rid of the complex fractions. So what we're going to do here, first thing we're going to do is we're going to multiply by the problem. The problem here, the main problem, of course, is the h plus 2 squared. So we're going to multiply by h plus 2 squared over h plus 2 squared. Now the 1/4 isn't a huge problem, but I still want to neaten it up because I'm a neat it up kind of guy. So I'm going to multiply by 4 over 4 because when I multiply through by 4, it's going to get rid of that denominator right here. Now I need to take this entire quantity, okay, and I need to distribute it to both terms. Now you also got to remember, like I said on the last complex fraction one, you cannot forget to take these factors and actually include them in your new denominator. If you don't, you're gonna get a wrong answer, and it's gonna look really weird. You're gonna beautifully simplify the numerator and have crushing defeat on this problem because you just forgot to do something that was actually really straightforward, but because you were spending so much time and effort making sure you got that numerator right, you fumbled the denominator. Okay, and that would be really sad. So let's be careful about that. Now when I take this whole thing and distribute it to that first term, the h plus 2 squared quantities cancel and a 4 is left. When I distribute it to the second term, the 4's cancel and the h plus 2 squared is left. And I'm left with h plus 2 squared times 4. Now, the only way to really do this now is we have to go ahead and multiply. We have to go ahead and FOIL out that h plus 2 squared in the numerator, because our only hope of getting this out of an indeterminate form is to get rid of that h down here in the denominator, okay? And the only way to do that is to free up this h from those parentheses. So I'm going to get 4 minus h squared plus 4h plus 4, all of that over 4h plus 2, and all I did was change the order of the denominator. Now what I'm going to do here is I'm going to rewrite that numerator such that it helps us a little bit. Now 4 and 4 are going to cancel because that negative is going to be distributed. And what's going to be left is negative h squared minus 4h, or negative h plus 4 over h plus 2 squared times 4. Sorry, I copied the denominator from here instead of over here, but you get the idea. That h cancels with that h, leaving a negative 1 factor. And when I plug in 0, I'm going to get negative 4 in the numerator, and I'm going to get what? Plug in 0 into here, I'm going to get 16 in the denominator. That is an answer of negative 1/4. And I don't believe I made a arithmetic error anywhere in there. It's always possible, but you do understand the general gist of it, I hope. Okay. Now, I think that's it in terms of evaluating limits analytically. If you have any more specific questions, or if you want me to go over any of the questions that your teacher assigned you for homework, please do send those to me. I cannot emphasize enough the fact that this is going to be a better experience for you guys if you do communicate with me a whole lot, okay? I sent you an email today with a couple of questions. I need you to go ahead and answer those questions, even if you're like, oh no, surely somebody else will. No, the only two people I've really heard from are Tim and Ricky, and that's about it. So I need y'all to communicate with me, guys, so I can make sure that this is helpful as much as y'all want it to be helpful. I desperately want this to be a good experience for you guys. I want to be as helpful as I can be, but I'm going to need some feedback from y'all. I hope the video helped. If it didn't help you in all regards, or if you want me to do more problems of a specific variety, like I said, either comment on the blog post that the video is attached to, or shoot me an email, reply all to the email that I sent out, whatever your fancy is. But I'll go ahead and line up. I need to do a couple of more videos today. I'm going to do the continuity one, and for the BC kids, I'm going to do the squeeze theorem one. So, I hope it was helpful, guys, and I will see you tomorrow when we will have more fun with math.